Good morning, everyone. I'm very excited to talk about our work, mini-batch serialization, CNN training with interlayer data reuse. As one of the speakers actually mentioned, training a modern CNN is a challenging problem. Well, it's mainly because it's already large and ever-growing data set size and the high complexity of network model. To accelerate such complex CNN training, a cluster of expensive accelerators with luxurious object memory system is actually used. So in this work, we actually challenge the need of expensive high bandwidth memory system for CNN training. So before that, let me talk about the data reuse opportunity in CNN training. So in forward propagation, the features extracted by convolution layers are getting feed-forwarded and reused between layers. And they are stored to object memory to be reused in the back propagation to calculate the local gradient. And then in the back propagation, the loss calculated at the end of the network actually getting back propagated and reused between layers. And the convolution layer in the back propagation has two phases, and their inputs are reused between the phases. And those normalization layers in forward and backward propagation actually use their inputs multiple times to calculate mean, variance, normalize, and also calculate their gradients. So in short, CNN training shows abundant data reuse opportunity between layers. However, capturing such interlayer locality in CNN training seems to be kind of challenging because of the conventional CNN training mechanism. Or mini-batch stochastic gradient descent is a very commonly used CNN training algorithm, and they have following benefits. Using a large mini-batch can increase the data parallelism at each layer in the network and reduce the number of model updates per training epoch, and then also it improves the stability of model updates. However, it also linearly increases the data footprint of each layer, so actually makes the reusing the interlayer data interlayer data is kind of difficult. And this graph here shows the size of interlayer data, which will be the features, and then the parameters per each layer used in RegNet 50. And here I use 32 samples per accelerator and floating point 16. So as you can see here, since their interlayer data size is too big, even using about 10 megabyte on-chip buffer space, we can only capture about 9% of interlayer data locality, which causes lots of expensive object memory traffic. So we can think of serializing a mini-batch as an easy solution. So we can propagate one or more samples, which I call like a sub-batch, through the whole layers, which here the size of sub-batch is actually fit on the on-chip buffer for all the layers in the networks. Even though we can capture the interlayer locality for all the layers in the network, this causes a problem because it reduces the data parallelism at each layer. It can actually affect the processing element utilization in the hardware. And also it actually requires many weight and weight gradient refetches because they are actually used between the different sub-batches. So our proposed mini-batch serialization mechanism, which I call MBS, actually partially serializes the mini-batch by adapting the size of sub-batch for different layer context. This is based on the fact that CNN has many downsampling layers. So basically, the later layers actually have a small volume of feature maps. So we basically increase the size of sub-batch for the later layers. So this actually can increase the data parallelism and also the intra-layer weight reuse for the later layers. So let me talk about how MBS works. So we first calculate the on-chip buffer space requirement for one sample for all the layers in the network. Here I use RegNet 50 as an example. So as I said earlier, since later layers have smaller feature volume, their on-chip space buffer requirement actually is smaller. And next, using this information, we calculate the minimum number of sub-batch iterations, which is actually the opposite of the maximum sub-batch size we can actually use for different layers. So later layers can use much bigger sub-batch, so they can need to iterate a small number of times. And now we merge those layers with same number of sub-batch iterations into one layer group. So within each layer group, the same sub-batch is propagated and iterated. Even though this approach actually can maximize the data parallelism and also intra-layer data reuse for all the layers without actually refetching the data, interlayer data from the object memory, they actually have some problem because their first layer in each layer group has to fetch their inputs from the object memory. So we rather actually merge those layer groups into a bigger ones by forming a bigger layer groups by using a greedy search. How it works is like, so we basically estimate the memory traffic cost of merging two adjacent layer groups, and we only merge them when the actually cost goes down. So eventually, for RegNet 50, we have 4 groups, and this MBS mechanism actually balances the interlayer and intralayer data reuse. So let me use another figure to actually better describe how MBS reconfigures a training graph. So the graph on top is the conventional mini-batch-wise data propagation. Since their on-chip buffers, since their on-chip buffer space requirement for propagating all 32 samples is too big, they actually cause lots of data fetches from the option memory, which is indicated by the red arrows. And after byte reconfiguration by MBS, now we have 4 layer groups. And within layer group, the same cell batch is actually getting forward propagated and iterated. And there's only option memory accesses for the rows, the data, at every first layer of each layer group. If we zoom in those like residual module in RegNet, it looks more obvious. In case of the original graph, we basically have to fetch the inputs for all the layer from the option memory. But instead, in MBS, we only fetch the inputs for the very first layer in the very first layer group, removing lots of option memory traffic. And in backpropagation, we don't need to store their outputs to the option memory, so it actually removes more memory traffic, and then it actually slightly has a different grouping configuration compared to the forward propagation because their data reuse pattern is slightly different. And MBS also further saves the memory traffic by reusing the data between branches. As modern CNNs have many multi-branch modules, such as residual module and inception module. And as you can see here, between branches, they actually share the same node. So between branches, they have to fetch their inputs or outputs. And since MBS can serialize the mini-batch, and then they can easily allocate additional space on chip to store those shared data, so we can remove those traffic and further saves the option memory traffic. Although it looks good, it has 2 major challenges to realize MBS. The first thing is the feature normalization. The most commonly used batch normalization requires to propagate all the samples in a lock step. So it basically adds synchronization points across all mini-batch. And also, even though we actually can use bigger sub-batch for later layers, still the early layers has to use a small sub-batch because of their large feature volume. So first, instead of using batch normalization, we actually use group normalization along with MBS. And unlike batch normalization, which actually normalizes the feature data across the batch dimension, group normalization normalizes the data within a group of channels, which is conventionally used for the object detection networks, which has a huge feature data, a feature map size, but we actually adopt them to the context of MBS here. To use them on MBS, it requires additional operations, which is reducing the per channel group normalization parameters across sub-batches. But since their size is very small, it adds very negligible performance and memory traffic overhead. We also evaluated their training accuracy using batch normalization and group normalization MBS, and they show very comparable validation accuracy. And before getting to the problem of the parallelism issue, so let me briefly describe the baseline computing core that we actually used for MBS. So we use 128 by 128 2D historic array for high data reuse, which is the same configuration of recent TPUs. And each processing element, this historic array, actually use mixed precision, floating point multiplication and add operation. We first convert the small convolutions into a GEM, which is a general matrix and matrix multiplication, for efficient execution on data parallel architecture, such as historic array, using image to column. So here we have 2 input matrices for the GEM, which is filters and features, and their configurations, their dimensions, M and K, are constructed by all convolution configurations. Then we tile the GEM to process on the historic array, here I show this toys historic array figure here. And then we use a weight stationary data flow in case of forward propagation. And how it works is like, so we first preload the weight onto each processing element in this historic array by shifting them vertically down. And when they are fully loaded, now we shift the feature data across the historic array. And then I call them a historic wave. So within each processing element, they actually conduct mixed precision multiplication and accumulation, and their outputs are merged by shifting them to downward all the way to the bottom of this historic array. And at the bottom of historic array, there is an accumulation buffer. It actually accumulates the partial output, partial sum of the previous historic wave to the current wave. So now getting back to the parallelism issue of early layers, which has to use a small sub-batch. So if the bottom line is that if one of the gem configuration, MNK, is smaller than the size of historic array, then the processing elements are hugely underutilized. But it seems like using MBS along with the gem convolution is a pretty good match, because as the table shows, all gem MNK dimensions for forward propagation and the 2 convolution phases in backward propagation, the red text, which shows the dimension using the sub-batch size, actually effectively multiply by large feature maps for the early layers. So basically, they create a large number of historic array entities maintaining high processing unit utilization. And then I told you that we use weight stationary data flow for the forward propagation in case. But it seems like it actually causes idling of many processing elements because it requires preloading matching weights for each historic wave. As the figure here shows, the waves which coming from the top to the historic array is actually matching weight for the following historic wave, but it can only shift it into the historic array after the current historic wave finishes its operation. So basically, there is a historic array height number of idle cycles between waves. So we basically add additional register to double buffer the weights for the current wave and the following wave. And then we use additional register selection signals for weights and then features. So now in the new figure on the right shows that the weight for the following wave can be actually shifted into the historic array even before current wave is fully processed. So it basically removes all the gap between 2 historic waves. So I so far described historic array cores to build wave core accelerator to efficiently execute mini-batch serialization. And I use 2 of those cores to link by NOC. And I use global buffer size of 10 megabytes using 32 banks to avoid the bank conflicts. And then I double buffer both the input buffers of the feature map and also the feature filters. And then I triple buffer the accumulation buffer to actually concurrently execute some additional operation required for MBS. And I use HBM2, which has maximum throughput of 300 gigabyte per sec as a baseline memory system, which is a little slower, but because MBS doesn't require that much of object memory traffic. And I placed the vector computing array right next to the global buffer to fully utilize their bandwidth. So I estimated their area using 32 nanometer technology, and then it shows like 524 millimeters square, and the maximum throughput is 45 teraflops. So I evaluate our proposed idea using our developed simulator, and then we use mini-batch size of per processor is 32 and floating point 16, and we evaluate them for 3 popular networks and using ImageNet. And then these are 5 configurations we evaluated compared to the baseline. PE double buffering does the bubble buffer the weight, so to remove the inter-wave P idling, and naive interlayer data reuse, basically reuse the interlayer data only when the entire mini-batch can actually fit on the on-chip buffer. And full serialization propagates the same sub-batch across the whole layers, which I talk about as a naive mini-batch serialization, and MBS is our proposed mechanism. So this graph shows the DRAM traffic per training iterations in gigabytes, and for different networks and configurations. And the line graph shows the normalized memory traffic. And since I mentioned earlier, naive interlayer data reuse only can reduce the memory traffic by 0.8x because most of the layers, their interlayer data cannot really fit on the on-chip buffer. And full serialization further improves the memory traffic by 2.3x, and our proposed mechanism achieves about 4x memory traffic reduction. And this shows the per training iteration execution time in milliseconds for different network and configurations. And those 2 line graphs shows the normalized speed up compared to the baseline and the P double buffering. And P double buffering improves the performance by 0.15x by removing the gap between two waves. And then, the full serialization improves the performance by 1.28x compared to the P double buffering, and MBS achieves further by 1.5x compared to P double buffering. And if you look at closely to the result for inception V3 and V4 for full serialization, their speedup is much lower than the legendary case, because they have to propagate much small number of sub-batch at a time, and then they actually cause more number of weight and weight gradient refetches, which affects the performance. And lastly, I show the energy comparison, and this shows the energy per training iteration in joule. And then, unlike the other configuration, MBS achieves about 36% energy reduction. The region is actually smaller compared to the other ones. It like still does all the computation required for the training iteration, and its major gain comes from the reduced traffic and the reduced static energy. I also evaluate our proposed ideas on different buffer size. So here, this graph shows the execution time and memory traffic for three different configurations using 5 different on-chip buffer size. So compared to the other configurations, which actually show much bigger degradation in performance and also memory traffic, MBS shows very stable number, even using small on-chip buffer space of 5 megabytes. So this carries the important message that MBS can be actually enabled using the interlayer data reuse, interlayer locality, even using a very small on-chip buffer space. And next, we also evaluate our ideas to different memory bandwidths. So here, I use 3 different memory types, HBM2 and GDDR5 and LPDDR4. I just vary their number of chips to match their capacity. And the memory bandwidth of a GDDR5 and LPDDR4 compared to HBM is about like 60% and 40% respectively. And their relative cost is like this. And the graph here shows the per training iteration execution time in milliseconds for 4 different configurations and 3 different memory types. And the line graph here is relative speedup. And compared to the other configurations, which actually shows a huge degradation in performance using smaller on-chip buffer, the off-chip memory bandwidth, MBS shows very small gap and variance between different memory bandwidths. And as you can see here, even using LPDDR4 with MBS still can perform better than P double buffering and shows a very comparable performance with naive interlayer data reuse. So this makes this actually says that MBS can enable using cheaper but much more bigger memory for CNN training. So let me conclude my talk. So basically, I introduced MBS here to enable the CNN training with interlayer data reuse, with small on-chip buffer and much cheaper but larger off-chip memory space to enable using much bigger batch size. And we do that by balancing inter and intra-layer data reuse using MBS. And we also introduce a wave core accelerator to efficiently execute the MBS graph. And it achieves 4x memory traffic reduction and 1.5x performance improvement. So as a high-level message, well, I think it's a collaboration of algorithm scheduling and architecture can actually make DNM training more efficient. Thank you. And I can open for the questions.
Okay, go ahead. Hi, I'm Sharath from Expedera. I was wondering, how does this analysis applies to RNN or maybe MLPs? So talking about the RNNs, their interlayer data is a lot smaller than their model size. So benefit actually is a lot smaller. Yeah, that's actually validated. Yeah. Okay, and another follow-up would be, instead of using systolic array, if you actually consider any SIMD architectures, how would that look like GPUs? So compared to SIMD, the reason I actually chose systolic array is a more tricky problem because they have much bigger data, parallelism, right? So that's why I thought MBS can affect much more severely to the, computing unit utilization. That's why I chose it. But SIMD will be much. I guess that in case of SIMD, the problem will be also a little bit alleviated than this. Thank you.
So Jung Ho Won from Seoul National University. Thank you for a nice talk. My understanding is that you change the definition or use a different kind of type of batch normalization, right?
Oh yeah, I chose different normalization
Yeah,
technique,
different
right?
normalization. Did you use that different normalization for entire ResNet or the only kind of some part of the ResNet?
Entire ResNet.
Entire ResNet.
Yes.
Then can you apply your idea to existing CPU and GPU and achieve some, not similar, but some degree of improvement? I mean, you suggested new architecture and it's not real yet, right?
Yeah, I think the mechanism that I use is basically blocking the, the on-chip buffer space to the size of the, blocking the, the interlayer data buffering to the size of on-chip buffer. So as far as we know how much space we have in CPU, but the problem is like CPU is actually cache, right? So we cannot actually program. As far as we can program, we perfectly, the buffer them. But if CPU can provide the programmability on the buffers, then I think it's going to be more straightforward to apply them.
Hi, Cliff Young from Google. Excellent talk. I think you really put your finger on one of the fundamental issues we worry about in terms of getting the most out of these accelerators. I thought I'd ask about balance in design. It seems to me like your technique is great about trading off HBM usage versus on-chip memory size versus the speed of the compute units on the machine. But you didn't go meta. You didn't have a sense for what's the marginal return on having more on-chip SRAM, or if you could have a magic HBM that was twice the capacity or twice the bandwidth, or those sorts of trade-offs. Where do you think the limits are when we, 20 years from now, look back at building a perfectly balanced accelerator? Where should we be going for that?
Okay, that's a very high-level question. So I think there are many available, like, the papers actually showing the good match between the computation throughput and the memory capacity and the bandwidth. I think they probably just look at the conventional approach of CNN training or like RNN training. So in our approach, basically, we just try to just trigger a little bit to avoid that kind of requirement. But I probably have to think about it, but I haven't really thought about how we can actually extrapolate the requirement for this for future work. Yeah.
Thanks.
Okay, let's thank the speaker again.